Right, so we're going to talk about performance today. Last time we looked at profiling and how we can see that certain things are not right with our code, or where our code is spending most of the time or most of the memory. So we had an idea of how to find out what it's doing, but it's hard to know whether that's the best it can do and how to improve on that performance if possible. And so today I want to try and focus on that a bit. So if you found that a certain part of your program is the bottleneck, is where the most part of the work is done, there are kind of two choices you can make. You could say, well, that's for my current program, but it's not parallelized. What if I take that large amount of work that has to be done and distribute it over different cores? They can work on chunks at the same time, and that's the way to speed it up, and they'll work most likely if you do it correctly. But the other way is to see, well, even this one core, am I really using it efficiently? Am I using this system as best as I can? Because maybe there's things I can tweak just for the serial performance, or the performance as we're still using one core. So we're going to look at parallelization later in the course. But today we're going to focus on the serial performance. So we're going to look at code, at the serial programs, and see what can go wrong and what in terms of performance that easily be fixed. Now, to know what can be done, we have to understand a little bit better things about modern computers architecture. And so we're going to look at that first. So to start with computer architecture, you should always start with the von Neumann architecture, or von Neumann machine, which is the archetypical computer. And it really has only a few components. It was actually sort of a design for a computer by von Neumann when they were building one. It's not crazy. It makes sense. You've got some memory where you can store your data. You've got a central processing unit that has a control unit, which basically reads an instruction and tells the other units what to do. And then you have some logic or some arithmetic units, so things that can do arithmetic or can do if-then statements. Now, in addition, you'll need some sort of input device. That turned out a little bit gray here. An output device, probably disk, or I don't know. At that time, it wasn't the internet. And so that's the basic idea of a computer, and it's still true. We have memory in our computers, and we have CPUs, and we have input and output. So with that picture in mind, I've put a little snippet of code here to see what we would imagine the computer is doing if this is what a computer looks like. So I have a constant int n that is set to 1 million. I would imagine that that's an n, that's a variable, so it lives somewhere in memory. So we've allocated some memory, and we store that value in the memory. I have two arrays. I'm being a little bit short here. I'm using automatic arrays rather than dynamically allocated for the point that I'm making. It doesn't really matter. So this is going to reserve probably some memory. So somewhere in this memory unit, the control unit is telling the memory unit, hey, I want 1 million integers. Integers are typically 4 bytes, so that amounts to 4 million bytes. And then I do it again with B. I want another variable C, so probably I'll have to reserve some memory for C. And then I have a little for loop that fills in the values of I. So I'm just going to store value 1, 2, 3 in these million elements of A, and then the value 929 in the million elements of B. And then once I've done that, apparently I want to add the 9th and the 4th element of these two arrays and put it and store it in C. So that's kind of what you imagine. That's kind of what the code says, right? You have some memory, you have some instructions, you act on that memory. So turns out that this picture actually doesn't really reflect very well what the computer is really doing. It promises to act as if this is true, as if this is exactly what it's doing, but it doesn't. So if we don't understand what it is doing, we have no chance of improving its performance. So having this instruction and memory picture alone is really not good enough to get an idea of performance. It's a first attempt. It's something that worked maybe in the past when architectures were a little bit closer to this Neumann architecture. So we're going to try and get a better picture. And there's quite a few parts of modern architecture that would come into play here. We'll talk about a thing called the memory hierarchy. So there's not one memory, there's actually several memories. We'll talk about registers, cache. We'll talk about file I/O. So how do you treat disk? We could talk about NUMA, which is non-uniform memory access, which happens on multi-core machines. We could talk about vectorization, which is a way of doing more than one thing at the same time with one core. We can talk about multi-core CPUs, network clusters. This is way too much to do in this 1 hour, and we can't do that. So we're going to leave the last 4 topics for when we're doing parallel processing, and we're going to look a little bit at the top 4. Here's the memory or storage hierarchy. Whenever you want to store data, there's different spots that it can come up in. Even just memory itself, you could easily divide into 3 different types of elements. Registers, which are very fast, they're basically memory in the chip. Cache, which is a faster memory, and not so fast memory is called RAM. And then there's different types of hard drives, flash drives, hard drives, and tape. And what I've put in this table is 2 numbers, and they're distinct features of any storage system. It's the latency and the bandwidth. So the bandwidth is usually what you get reported because it always impresses. You can get 50 gigabytes per second out of your CPU cache. Well, that's a lot of pretty quick. You can get 10 gigabytes per second out of your slower RAM. You can get 250 megabytes per second out of your flash drive versus 100. But one thing that really matters, especially if you haven't optimized your code yet, is latency. So bandwidth is really the speed at which you get data once it's flowing. The latency is how long it takes for this flowing to start. You can imagine that every time you ask for some data, imagine that it takes some time for that request to be processed. That's essentially the latency. So when I ask for some memory out of this cache memory, it takes about 5 nanoseconds to even get started. Once it's started, it could sort of flow at a rate of 50 gigabytes per second. And the latency part is what really drives things insane. So for a hard drive, it could take 5 milliseconds before I even get anything done. For tape, this is really just a bogus number. Tape typically goes into a tape drive, so it just depends on how long it takes me to get the tape from the shelf and put it in the drive. That could be a minute, but I might have something else to do. So it's almost human scales. Or I might have a robot, but that still takes a certain time. Okay. So in this hierarchy, we can look at the scale from the CPU operations to tape, and we see many orders of magnitude difference between those different storage systems. So we really want to be we will want to be careful in where our data lives within this hierarchy, because it can take our application from taking a second to taking a century. Now, this hierarchy exists, so we don't just have one big von Neumann memory, because it's basically way too expensive to make everything as fast as possible. I kind of did a back of the envelope calculation that if you wanted to get your fastest possible memory, so the sort of cache level memory, and you wanted to get 256 gigabytes, you'd probably pay about $1 million. Now, nobody's going to buy $1 million memory controller or memory chip, and so nobody makes those, right? But that's why they're slower storage. If you just wanted your RAM and you wanted 256 gigabytes, and really these are very rough estimates. This is probably not quite correct. You probably can get it for cheaper if you ask nicely, or for more if you want more performance memory, but around $5,000. So it's about a factor of 200 less. And if you just want to store stuff on tape, you probably can get it under $50. So, depending on how high performance you want it, there's a cost. Okay? So most systems have a hierarchy. They have some of the fast stuff, some of the slower stuff, and some of the real slow stuff. And you will have to decide where things should live. So let's start at the top. Registers. You can think of them as very fast pieces of memory. They're kind of part of the CPU. So CPU can do things like add two numbers. It'll have to have those numbers stored somewhere before it can add it. It has to know them. So it stores them somewhere in the chip. Those are the registers. And so essentially, because they're already on the chip, there's no latency involved. They are already there, right? Once they're there. So anything that lives in a register is instant access, as far as, for all practical purposes. Now, I want to compare this with the access time of other bits of memory. So I'm going to make up a number saying that I have a machine that has a clock speed of 4 gigahertz. So every second, 4 million cycles are done, or 4 million somethings are done, which means that my access time is effectively 1 over that. So 0.25 nanoseconds. Let's just say. Now, that's nice and fast, and this is the $1 million bit of memory that I was talking about. But since it's part of the chip, first of all, you can't put too much on that because the chip would be huge and costly. But also it's fixed. And typically you only have a couple of these registers, 16, 32, 48. It depends on the CPU architecture. You don't have any control over it. You buy the chip. This is how many registers you get. Any other data that you have must first be loaded into a register. So if I want to add two numbers and they live in memory, I have to load them to registers and then add them. Now, we don't do that. Yes? No, I mean 16 numbers. So usually 16 32-bit registers, yeah. Right, so any data that we want to use first has to be loaded from memory into these registers, and then they can be added. That's typically how it works. Not every instruction is the same, but that's typically how it works. And we're not doing that ourselves. We let the compiler do that. We let the compiler know what we want to happen, and the compiler says, okay, I can store this in that register, I can store that value in this register, now I can add them, they come out in another register which I can store. All of that is the compiler's job, it's not our job. But it's good to know that there's only a limited number of these registers, and that if it is in register, things will be very fast. So once we've run out of registers, we'll want to access memory. And so even on the chip itself, apart from these registers, there's some sort of bit of memory called cache memory that's baked into the CPU. Now, cache is very funny, as we will see in how it behaves. But let's just pretend for a second that it's just regular memory. Usually you have at most a couple of megabytes, and that's on a good chip. It could even be under a meg for the cheaper chips. But it acts as an intermediate memory, so it's pretty fast. But fast is expensive, so that's why you only have a few megabytes. Now, if you have a computer that has gigabytes, how does it use those gigabytes? Well, it copies something from those many gigabytes into cache. So it's an intermediate memory. And it's all automatic. You do not control any of the copying in and out. You can give some hints, but you don't copy out or in these things. And that makes it even more important to understand how it works. Your code is translated by the compiler into something that uses registers and memory. The compiler cannot say, because you can't say, what is copied when into cache. There's some exceptions, but by and large this is true. And so we have to understand what happens when this copying happens to understand what's going wrong, which might go wrong. Then at the end of the memory hierarchy is RAM, or main memory. That's the memory that you talk about when you say my computer has 4 gigabytes of RAM. That's this RAM. It's called main memory. It's the slowest of the non-persistent storage. Non-persistent meaning is when I switch off the computer, whatever was in memory is gone. And the access times are of the order of 100 nanoseconds. So that's almost 3 orders of magnitude slower than my chip. So we want to be careful with this. It's not tied to the CPU, so that's good. You could usually add memory if you don't have enough memory. So you could get a box with 512 gigabytes, and you could do that. But it would be this slow memory that has to go through cache and then to registers for it to be useful. Okay, so those are the 3 stages. And then after that comes persistent or non-volatile type of memory. You can have a solid state drive. It has access times of the order of a millisecond. And typically they're a little expensive, so you wouldn't buy them for more than a few hundred gigabytes. It's not that you cannot get them bigger, but they become really expensive. Hard drives are based on spinning disk technology, and they have access times of the order of several milliseconds, and their bandwidth is not as big. And you can understand, see, a solid state, everything is just frozen, so you want something, you just go and get that byte, more or less. With a hard drive, you have to wait for that byte to come by, and so the faster your disk spins, the faster it will be, but you still have to wait. You can get pretty large drives, so that's good. You can combine them together, get network storage, parallel file systems. So you can get a lot of storage, but it's not fast. Okay? So if you have a lot of data and you have to read them from file and don't fit in memory, that's just your reality. You're here. But when your data isn't large, say it does fit, you have a gig of memory of data, and that would fit in memory. So sometimes it makes sense to go, okay, I don't want this to live on the disk. I want to have it in memory. And this is especially true if this is, say, temporary data. It could be sort of tempting to say, well, I'm going to see what my code is doing, so I'm just going to write all my arrays to disk to check them later. And basically all that your program might be doing is doing the disk I/O to write these arrays. So that's not always a good idea. Tape is even worse. It's actually not as bad once the tape is in the tape drive, but as I said, it really all depends on how long it takes before the tape gets to the tape drive. And if you have some sort of shared resource, like we have at SciNet, where we might have a whole bunch of tape drives, they're still going to be busy with other users, and now you're in a queue waiting for that. So it's a kind of offline, even if it's automated, kind of offline or at best nearline kind of data. But capacity is very cheap. So, and what's nice about tape, the one reason why it is so cheap is that once you've written it to tape, take it out of the drive, put it on a shelf, it costs you $0 while it's sitting there. The spinning disk, you still pay for the electricity as it's spinning. That makes tape that's why tape is still around. It sounds like might sound like an archaic medium, one of the first mediums, but still around because it can hold so much at very little price. So that's the end of the hierarchy. It goes all the way from nanoseconds to seconds, and it matters where things live. So if your data is not at the fastest possible spot, your performance will suffer. So we're going to see how, and basically you're basically suffering the latency the most in most cases. We're going to look at two aspects in particular, and we'll do the last one a little bit slower, a little bit more cursory perhaps, because there's less to understand. File I/O, we have a feeling for what files do. I just want to pinpoint a few things that you might not be aware of. But the cache behavior is something that we want to look at. Sorry for the US spelling here. The cache behavior is something that we really want to, we need to understand a little bit better because it's not trivial. Okay, so we have this hierarchy. We do it because there's costs involved in not having the hierarchy. How do we still get the best performance? And how is this hierarchy working behind the scenes? So how's cache work? So, as I said, we have slow memory, the main memory for storing our data, and we have this small high-speed cache as a working memory. Now, if we just have temporary data, say we make a small array that fits into cache, we work on it, and then out comes one number, that small temporary data can just live in cache. So now that's great. If our data is small and it doesn't have to be stored, we can just permanently. They can just stay in cache. We get all the benefits of this cache memory. But it won't be much because we only have a few megabytes. So what about larger data structures? So now it gets complicated. So this larger stuff has to be in main memory, doesn't fit in cache. So what happens is that every time the CPU asks for a bit of memory that is located in main memory, it maps it into cache. In other words, it copies it from the main memory into cache. Okay? Now, if that had to happen for every time we access main memory, we copy from main memory to cache and then into register and do something with it, then we might as well not have cache because it's probably faster to just copy from main memory directly into registers. Right? So the way that this gets any sort of benefit is by not copying byte for byte, not copying for every access. So we don't want a one-by-one copy of 64 bytes, say, if we have a set of 64 bytes, 8 doubles or something. If we want to know how long it takes to get that, and we do it byte by byte, we have the bandwidth to worry about. We also have the latency. So for every byte, I would get a latency. But if I do it as a big chunk of 64 bytes, I only get once the latency and 64 times the bandwidth. And in that case, the added bonus of having a fast working memory versus just one latency that hits us here is worth it. So we want to do this. Now, how does this get done? As I said, it's automatic. So it actually turns out that this always happens. You always get a cache line that's, let's say it's 64 bytes of contiguous memory at a time. Whenever you try and access any byte in the main memory, it doesn't copy that one byte, it copies 64 bytes around it. So, and it only does that when the data is needed, right? So that makes sense. So it only does that when the data is needed. Every time you need data, it copies what's called a cache line, these 64 bytes. Could be more, could be less, depends on the architecture, but 64 is pretty common. And so whenever you want to access memory, the first thing that the memory subsystem does, without telling you about it, is to see if it's already in cache. If it is, it's not going to get it. So if you have a way in your algorithm to reuse data while it's still in cache, it won't have to be retrieved, and so things will be faster. If not, you have what's called a cache miss. Now you always have some cache misses, but you want to get not too many of these. Now it turns out that when you get these 64 bytes, you don't just get the 64 bytes from the point where you started, but they kind of have to be aligned. So if you ask for something that's at address 3, you will get elements 0 to 16, where 3 lies in the middle. It has to be aligned to a cache line. Now that's how it gets stuff, but no, cache is limited. So at some point it'll have to discard some of the old stuff. So when cache is full, when you ask for some memory that wasn't in cache, but cache has been filled with cache lines, it just basically releases one of the cache lines. It reuses part of one cache line. Now there's different ways and different strategies that can do that, in which they can do that, which I won't go into. But you read 64 bytes. Things are, the processor memory subsystem really reads 64 bytes. We're full. We just overwrite the oldest one. The idea is that if it's old, it probably won't get used, and things that are there still are probably going to be used. Okay. So, for instance, if I had an array of 100 doubles, if I ask for element A0, it'll also load A1 until A7, which will give me 64 bytes, 8 times 8. Which is fine as long as sort of the next element that I'm handling is A1, and then the next element is A2. So if I access things in sequence, in the way that they are stored in memory, I'm using the cache. If I don't, and we basically get 8 transfers for the price of 1. But if I don't, if I say jump from A0 to A16, then that's on a different cache line, and that cache line has to be gotten separately. So I get hit by this cache latency twice, or every time. Okay. If it's not cache aligned, you get something that goes around it, but it still works the same kind of way. So the way you can optimize knowing this is to make sure that you reuse any data that is in cache. So if you know that you've accessed an element, you know that you have the next 63 bytes as well, or the next 8 elements in the case of doubles, or the next 15 elements in the case of integers. If you can rewrite your program such that it uses those right away, you're in business. If you didn't, you might get a lot of cache misses, and you might pay a large penalty. So with this in mind, let's look at what really happens in this code snippet that I showed before. So here again we have n is 1,000,000, 2 arrays A and B, they get filled. I have an integer C, and the C gets the result of an addition of 2 specific elements from these arrays. So the first statement, int n is 1,000,000. The integer is small, so it would probably fit in cache. We're assuming that it doesn't get used somewhere else, so that would be fine. But in this case, actually, because it's a constant and it won't change, the most likely thing that the compiler would do with this is just say, well, wherever I have n, I'm just going to substitute literally 1,000,000, and then don't have to have it stored for that. I can have so basically the CPU can deal with literals. So that probably doesn't. Yeah. No, so basically the constant don't cost you anything, typically. No, but so it could be using a register only if, so this is the compiler's decision. If it makes you could run out of registers, in which case it would have to now start storing it in main memory, and things would progress. But more than likely, it wouldn't even waste the register for this. It would just say, well, and wherever it is, I don't need a variable for it. I don't have to store it. I just say do this 1,000,000 times. So this probably doesn't cost us a thing in terms of memory. Here come our arrays, and let's assume that our cache size is 1 megabyte or less than 1 megabyte. Then these arrays of 1,000,000 integers must live in main memory. So yes, memory would be reserved. It'll probably not really be reserved until you use it, but that's a detail. It will be reserved in principle in main memory. And then we have this other variable C, which is again small enough to be in cache, but really because we haven't used many registers here as far as we can see, I'm going to guess that C lives in as a register. So again, it doesn't cost us anything. C is going to be pretty fast. So let's look at the loop. So the loop goes through the array. I, again, probably in register, because it doesn't do much. At the first iteration, I'm asking for A0, or I'm going to store A0, which is essentially the same thing. So I'm going to do, so the cache is going to do a mapping from main memory to cache. It'll get 64 bytes, so that will be, in this case, 16 elements. They weren't initialized, so there might be some cleverness that happens where it goes, I don't really have to copy it, I just have to know that it is there. Anyway, those are details. It essentially made this mapping between main memory and cache here. Now, when I do a second iteration, so I is 1, then I already have A0 in cache. Okay, so it doesn't do yet another load. Only when we reach I equals 16 do we load the next cache line. At some point, I didn't do the math, but 1 megabyte divided by 64, whatever that is, you will get that the cache is depleted. It'll throw away the old stuff and it'll put in new stuff. Yeah. It depends on the details. Usually not. In this case, well, let's put it this way. We'll see in this case, it won't be slower. But in the general case, when you have 2 arrays to deal with rather than 1, you think, well, basically my cache is halved, which is true. But typically the lines of one array will not overlap with the other ones, so they kind of have their own dedicated. Well, not dedicated, but so a cache line from A usually doesn't get kicked out by requesting B. They map differently. Anyway, I'll explain in a second why it doesn't really matter in this case. Right. Now, once I have C, the last line, what happens is, okay, I want the 9th element from A and the 4th from B, or the 10th element from A and the 5th from B, really. Now, since I'm at the end of my arrays, more than likely these guys are now not in cache anymore. They're old cache lines, and so for both of them, 64 bytes will be loaded. So A from 0 to 16, and B from 0 to 15. And only those two values are used. Okay. So that is what really happens. Now, performance-wise, we're not going to gain much in this little code, but the mechanism of what is happening is quite different than just simply thinking of it in terms of memory. So let's look at a case where it does matter. So I have a two-dimensional array here, 3 matrices actually from like 8,000 by 8,000, so nice and citable, so they don't fit in cache. Has some constant k, and when how long it takes to initialize this matrix and to do some computation. So I initialize A by some constant divided by the difference between I and j, so how far away am I from the diagonal? Just something random. And B is similarly allowed. And then I'm going to compute A times B and put it in C. So I have 3 big matrices. One is one bit of code is initializing with the double loop, and the other is computing. And because of the tick-tock, which is a variant of one of the tick-tocks that we saw in the last lecture, we can see how long this takes. So it takes 4 seconds to do the initialization and 5.8 seconds for the computation. I'm going to change this code a little bit and ask you what you see. What is the difference? Spot the differences. Yeah. So the order of the I loop and j loop has been inverted. So here the j loop is first and the I loop is inner. And here the I loop is first and the j loop is inner. And I did the same for initialization and computation. So mathematically, there's no difference on how I traverse I and j. I'll just give the same result, but the performance is quite different. The initialization here is about 3 times faster in the second case, and the computation is almost 10 times faster. Why is that? Any ideas? Yes. Yeah. Exactly. Yeah. Yeah. That's exactly it. So in this case, the first element I do is 0, 0. The next element I do is 0. Is 1, 0. But 1, 0 is what is n 800? Is 800 integers away in memory, right? So we're using here that matrices or two-dimensional arrays in C++ are stored in row major column, the row major format, which means rows are stored contiguously. And so I want to go first along the row direction, which is the first index, which is I, and then along the column direction. Okay. So the column index gets me from column 0, column 1, column 2, column 3. So that goes along the row. So if I have my column index go in the inner loop, I'm going nice small steps in memory, which means that I'm taking element 0, I'm getting the next doubles, the next 7 doubles for free. I don't have to load them anymore, right? And then once I get in element 8, I get the next ones. Whereas if I don't do that, when I load element 0, I get 7 other elements of that row, but I'm not using them. I'm going in the column direction. So that's why in C, you want to have your first index in the outer loop and your last index in the inner loop in this sort of way. And the difference in speed is remarkable. The reason that it's not so big in initialization is that it takes some time to compute the absolute and to do the division. Here, multiplication is relatively lightweight compared to all of this loading.
How can you apply this to other languages? So like Python or Fortran or what, like row weight?
In Fortran, it's just reversed. So things are stored in column major, which means that if I go along the columns, that's the direction in which memory goes.
Yeah.
So I will have to do exactly the opposite, where the first index should be the inner loop for Fortran.
Which language you're using and manipulate it.
Well, you have to know, right? If you don't know, you could measure, but for Python, you're probably spending more time computing the next element I than just doing so in principle the same applies, but yeah.
Isn't applying Python, I assume, kind of care of that for your writing? Because in
Yes.
Python, you're just going to vectorize everything and then.
Well, it's true, but that's only if you use NumPy array operations. If you start using explicit loops with your NumPy arrays, you're actually spending a lot more time doing all kinds of things. And these kind of low-level performance, while they're still valid, matter a lot less because now you're just waiting for the interpreter to do stuff. So
Right, I mean, it seems that you should never write using Python.
right.
It's very.
Yeah.
I've done that mistake.
Yeah, no, doing it purely using array operations in Python basically means that you put your loops into the C code that NumPy has, and then they have make sure that they do things in the right order. Make sense? So this is the only thing we've done here is really making sure that we access our elements in the right order. That's not the only thing you can do to use cache. The real secret in using cache well is to make sure that you reuse things. So here we're using every element only once. When we're using every element only once, and that element lives in main memory, it has to be at least once copied from main memory into cache. So the only thing we need to make sure is that we don't copy it more than once. If we use it once, we want to copy it once. In this case, we've copied it several times because each time we got to the same row again, we had to recopy it because it was now filled with cache lines from other columns. So we were actually reloading things n times rather than once. Here we're loading each element once, so we don't get that hit. But if you have any sort of algorithm where data is reused, a typical example is when you do a matrix multiplication, where every row and every column get multiplied. You basically have reuse of the same data. If you count it, you will see that in this case, every element is used once. In a matrix multiply, every element is used n times. So naively, you would think it would have to be loaded n times, but not really, because what if you could use that element when it's in cache, do everything you need to do with it while it's in cache, and not load it again and again. So it gets tricky. The only way you can do that is by sort of subdividing your problem, because if you want to load it only once, it has to fit in cache, and it doesn't. It's too big. So these kind of games, or these kind of tuning, while very powerful, is all done already in libraries. This is why we spend so much time talking about libraries that have been optimized. That's the kind of stuff they do. They make sure that algorithms that reuse data use it such that the cache gets hit as often as possible. You have at least a number of cache misses. So things like BLAS, things like FFTW, they use this stuff behind the scenes. Okay. So that is more or less at the top level of the hierarchy. But as you can see, you can easily get speedups of a factor of 10 if you did it wrong and now you do it correctly. So if your hotspot turns out into some nested loop, make sure your loop's in the right order, and just ordering the loops could save you. I want to spend some time looking at the bottom of the pyramid as well, file I/O. So we keep our data. If we want to keep it, it has to be somewhere where it's still there when we switch things off. So file systems is where we do that. It's usually spinning disks, but you could go to tape or you could go to SSDs. They have directories, subdirectories, files. At the end of the day, the disk itself is just a bunch of bytes, right? Everything else is described for it in terms of metadata. A file name is another set of bytes that's somewhere on the disk. Directory, same thing, right? So we're basically interacting with a file system or a disk system when we're doing things like opening files, reading files, closing files. And every time we try and do anything, we get hit by a latency for the file system. So we're going to work in units of these IOPS, IO operations, or IOP operations per second. Every time you do an IOP operation, you basically make a request to the file system, and it has to take some time. So some examples of different IO operations. If you're just finding a file or listing it, that's an IO operation. It has to go and read the metadata, the file size perhaps, or at least the list of files in it. It takes some time. It's an IO operation, actually several. Opening a file, you'd think that's, when I first started programming many decades ago, opening a file seems so unnecessary. The file is right there, it has a name. Why can't I just say, read from the file by this name? But what happens when you open a file is that as the file system checks if it exists, see if you are allowed to read or write the file, then find that file on the disk, say, okay, it's over there on that cylinder and that segment, and often starts reading or starts accessing the first part of the file. Okay, so opening a file isn't nothing. It involves a whole bunch of stuff. Reading a file means getting to the right spot of so say moving the head of this moving spinning disk to the right spot. Read a block, much as in cache, it typically reads a whole block at a time, and then pick out the right part from that block. So that's not particularly free. Writing to file, not only do you have to find a spot, you have to find space on the disk, make sure that there is space, do any sort of admin stuff to make sure that that piece of the disk knows that it's part of the rest of the file. And every time you do any of these, all of that has to happen. You might have a sort of seeky behavior where you say, well, I now want to write into byte 10 of my file, so you set your file pointer to byte 10. You can do that. Again, now the file system has to check where that really is, so that it costs some time. And even closing the file costs some time, because these typically there's some caching behind the scene. The last block has to be written. Metadata has to be updated, so file name, timestamps, that kind of stuff. So all of these are operations that aren't free, particularly, now you would mention reading and writing not to be free. That directly affects your data. You're reading data, of course, it costs some time, there's some bandwidth. But even the idea that opening and closing a file costs you some time is good to know. Now, why does this matter? Why do we need to talk about IOPS? Here's a little graph that is supposed to show this. It's not quite up to date. It goes to 2010, but the line here shows the average drive access rate, so megabytes per second. And it's gone up quite nicely over the years. But it doesn't go nearly as fast as how fast our CPUs go. So this is the slope of how fast CPUs go. It's not the absolute case, right? So the absolute case is actually even higher. Which means that basically, relatively speaking, not only are the disks the slowest part of our hierarchy, they are getting slower and slower. In other words, they can't really keep up. So all of these ideas of this costing you some time, some latency, becomes more important because we want to, if you get a system that is, say, 10 times faster, but our disk is only 2 times faster, our system becomes only 2 times faster if we're not careful. So we have to be sure that we hit the file system as little as we need to. Oops. So here are some tips on doing that. One immediate tip is to use the right format. If you write in ASCII now, and we've done that in the examples, it's slow. And I'll show you some numbers as why it's slow. You want to use binary formats. It's a native format in which the file system stores things. Use it. If you're doing things on a supercluster, try and use parallel I/O. If only one of your cores is writing at a time, the other cores aren't doing anything at the same time. If you have a parallel file system, use it. We have it at SciNet. You don't have it on your computer. On your computer, it's not going to matter. On our computers, it will matter. Other tips. Try and get files as big as possible. This sounds strange, but not if you think about the fact that most of the IOPS deal with metadata. The larger my files, or the least files I have, the less metadata I have. If I have to open only one big file, that's one latency for opening a file. If I have to open 1,000 files that are 1,000 times smaller, now I hit that latency 1,000 times. Right? So large files are better for that, and minimize the number of files. It also makes your file system more responsive. If your directory contains 100,000 files, you type ls, you're waiting for a little while. Okay, and it helps. So what you don't want to do is write ASCII files if you can, unless you actually have text to process. ASCII file is only really good for text. Don't write many hundreds of files in one directory. A thing that we're not seeing right here because it's serial performance, but whenever you write to a directory, it's a list of files. If any other process is trying to write to the directory, it has to wait until that metadata is updated. So you basically get file locks. It only really shows itself when you're doing parallel I/O, but it's a bad idea. Here's one that you once you see it once, you probably never do it again. But don't open a file, write one line, close it. Open it again for append, write another line, and close it. Why? Because that opening and closing, in between the close and the open, the system can't assume that nothing has happened to the file system because you're also logged in. You might be doing things with it. So it has to look again at the file system. Where is this file with this name? You might have renamed it. It might not exist anymore. So all of the checks have to be done. Again, when you keep it open, that's not the case. When you keep it open, you could try and rename it, and it probably, depending on the file system, would now write to the new name. It's a bad situation. You don't want to do this. You don't want to write to the same file at the same time. But at least you don't, but you could. Because you could, opening, closing costs you, or ask the file system to check again where everything is. So open once, write all your stuff, close at the end. Don't write many small files. Most file systems work better for larger I/O. The file systems on supercomputers particularly work well on large I/O because they're designed for it. And then finally, and I'll let you read through some of this later, but the file formats matter. So whether you do ASCII or binary, or use a library. So the difference between text and binary, there's a couple of things. The nice thing about text, or ASCII, or it stands for American Standard Code for Information Interchange, laudable goal, it's human readable. And that might be a very attractive thing. Like you write out your data, you could open the file and see if it's correct. That's fine if your file is small. If your file contains 1 million numbers, you're not going to read 1 million numbers, right? It doesn't matter that it's human readable. You're not the one reading it. So it's quite inefficient, and it is kind of expensive to do. If you wrote in binary, basically a raw dump of what's in memory, the storage is as efficient as it can be, and the read-write is also very efficient. The only thing is you have to know how things were stored in memory in order to read the file later. So just to give you an idea on the speed differences, here's writing about 100 million doubles in ASCII or in binary on SciNet. On our Scratch file system, which is a parallel file system called GPFS, if I write in ASCII, it takes about 170 seconds. To write in binary, it takes 6 seconds. So if you find your bottleneck is in I/O and you're writing in ASCII, this might be a hint to try and write in binary. Now, just to show you that it isn't just our file system being slow, which does happen sometimes, but that is not what's causing this here. I wrote to a directory called defshmem, which is a directory that lives in RAM. So you're basically writing directly to RAM, no spinning disk. It's pretty much as fast as you can. And the ASCII is just as fast. The fact that it's slower is a statistical fluctuation. So now I go from, now I only almost have a factor of 200 faster. If I wrote to disk, so an actual spinning disk rather than this parallel file system, things would take a little longer, but I would still have the same effect, about a factor of more than 10 writing in binary versus an ASCII. And it is because ASCII is not the native way in which data is stored. So I'm converting from a binary representation, which we talked about, to a decimal representation, which is, to make things worse, not exact. So use binary for anything that's numbers. I gave a few ways of doing this in C++. The offstream objects have a method called write that does that. And it just writes a block of bytes. Okay? That's one way to go for binary. You want this speed difference, right? Now, if you have profiled your code and you find that you're not spending any time in your output, that's not the time to start changing things, right? You change things when they need. But if you're starting anew, you might as well start correct or start in a good way from the beginning. The thing you lose with binary data, though, is that you have metadata to worry about. So the file system takes care of things of the size, where it is, who owns it, what time it was created, etc. But what you have to take care of is what kind of format is it? What's the version of the format? Where did it come from? You could store that separately in a little file, like an XML file or something, which is fine. Or you could use sort of standard formats. I'm going to look at this thing called NetCDF here for just a second. So it's a standard format. So the nice thing about using a standard format is that you can give this file to somebody else. They read the documentation and know how to read it, rather than you giving them a binary file of your own concoction, and either it's well documented or it's not. But in any case, it takes some doing to read it. There's a library for it, so people can read your files, and it's fairly flexible. And it builds metadata in here. So the way it does that is, suppose here's our binary data. If we just did a raw dump, we'd have to know things like what is the type of the data. If it's double, then each element is 8 bytes. If it's integers, it's 4 bytes. If it's floats, 4 bytes. But NetCDF demands not just that you store it given a specific type, so you tell it the type. It also stores the name of this. And it stores the dimensions. So you will know if this is a 2-dimensional array or a 1-dimensional array and what its dimensions are, because they have to be stored in there. And each of the dimensions even gets a name. So even if it's as simple as x and y, now you know which one is x, which one is y. This can help you if you're storing things in column or row format. And you can give some attributes, so some other useful information. And then that is one array that it would have stored. You can store more arrays. Those arrays might have relations in which they, for instance, have the same dimensions. So you can, instead of taking the dimensions inside of each of the several blocks, you just define them outside. And file attributes could be things like units or whatever you want. This is the idea of how you store a NetCDF. So everything has a name. It should describe what it is. The dimensions are known, the types are known. So now you can figure out how to read this data because you know basically everything there is to know. It all has a final. I've got some examples of how you do it with the NetCDF library, but you can look at it. So the advantage of using something like NetCDF is that it gains everything that you have from native binary, efficient storage, efficient read and write. But you gain portability because it describes what it is. It will even tell you if it's like how it's stored. And it embeds metadata. The only sort of disadvantage is that it really is aimed for multidimensional arrays. It's very good at it, but if your data isn't a multidimensional array, there are different things that you can use. Yeah. Sorry? Not by much, because if you think of the, like, presumably this is a fairly big array. So the fact that you also have to store one name and a couple of dimensions compared to probably a gigabyte of data that you have here is a small price to pay, because you still want to know what these things are. So somewhere it has to be documented anyway, whether you make a separate file and you write it in there, or you embed it with the file. And so if it's with the file, you can't lose it. So it's not really lost. Now, that's if you want to share this file. If this is a file that only this particular application uses, say you have a restart file, so it just wants to dump its array and then read it in again and start afresh, you don't care about portability. You don't care about this. So then you just do a raw dump and you do a raw read in. But you can't expect that file ever to be useful for anything but that. Not really. The only not really. The little bit of overhead here is not going to. Remember, it's still one file. So you open the file, that's only one, right? And so it becomes pretty negligible. Yeah. Okay. So just to conclude, when we want to look at memory performance, which is at the top level, right? We want to make sure that our data is where it should be. So we want data locality. When something fits in register, it should fit in register. When it fits in cache, let's make sure it fits in cache. So don't allocate an array that's just big enough and give it 1 billion elements just because. Try and do data reuse. You may or may not have the opportunity, but at least make sure that data gets used as it is in cache. And the way you do that is really to use the spatial locality, to use the fact that things are stored in a certain way in the memory and to access them in order. On the other side, for I/O performance, use binary data, make large files, or really don't make a lot of files. And again, use spatial locality. The same kind of ideas where it reads really a block at a time, which I didn't go into, can help you. If you just go into a file and you seek back or forth, you have the equivalent thing of having cache misses, essentially. So you don't really want that. Okay? So you're not going to hit all of them necessarily, but I hope I explained a little bit more about why or how you could tune a code by being aware of these things, even if the code doesn't seem to be doing anything different.